Hi everyone and welcome to our panel today. My name's Alex. So pleased to see so many friendly faces in the audience. We've got a fantastic panel lined up today. Dr. Katrin Woody is going to be moderating. I'm going to hand it over to her to let you take it away with the intros for the panelists. All right, thank you.
Okay, thank you very much, Alex. Hopefully the sound is okay. I'm not allowed to move due to the speakers. That's why I'm sitting here a little bit strange maybe, but hopefully this is okay. So Alex, thanks for the introduction. My name is Katrin Woody. I'm professor for laser-based additive manufacturing at the Technical University of Munich, and I'm the moderator of today. So if you have some questions in between, we would like really to engage you, to raise your hands, ask these questions, but we can also have a Q&A at the end of this session. So I have three guests here. Welcome from my side. And we start with a short introduction round. So Niels, you can start.
Yeah, thanks, Katrin. Yeah, my name is Niels Niemeyer. I'm based in the US, but happy to be here in my home country. I'm the general manager for DMG Mori Additive Solutions, meaning I support the entire portfolio from directed energy deposition to powder bed additive manufacturing in North America.
All right. Yeah, my name is Florian. I'm with the Conity 3D. We are a machine manufacturer with customizable solutions. So basically working with any kind of new laser beam sources and checking out their advantages is our daily business. So I'm happy to be here and share my experience with you.
Hello, also from my side, my name is Richard. I'm from the University in Nuremberg-Erlangen. At the Institute of Photonic Technology, we are focused on basically laser material processing and other optical technologies, also sensing. And yeah, I'm working in the area of powder bed fusion, especially on the topic of beam shaping, and I'm happy to be here today. Thank you very much for the invitation.
Okay, so thanks from my side. And I will start with a short introduction, let's say. And first, I have a question to all of you. So who is dealing and actually working with powder bed fusion systems? So running processes. Yeah, very good. A lot of you. So why we are doing beam shaping is on the next slide. There you will see a video. And for every one of you who is working with powder bed fusion systems, I think you have seen something like this before. The powder bed fusion process is a highly dynamic process. You see a lot of spatter formation. You see sometimes powder particles flying around. And therefore, from our point of view, the beam shaping technology and to tailor the energy input in space, but also in time, could be helpful to avoid some of the defects we are seeing here. And on the next slide, I will shortly explain because we are at the nLIGHT booth, and nLIGHT has one specific technology to shape the beam, but there are different ways to shape the beam. And the technology from nLIGHT is working with a specific resonator and fiber design at the end. There you can change the beam profile from a Gaussian beam profile to different ring-shaped beam profiles. But the variety of beam shapes you are able to create at the end is limited. And there are other beam shaping technologies which are more flexible. Let's say there you can change the design of your beam profile in any way you would like to change it. And one question we will have later on also for the audience is, first of all, what's the perfect beam shape? And the other question is, why are we doing beam shaping? And therefore, on the next slide, thanks, Rob, you see three different pillars we are covering today. And the first pillar is that we have some really great investigations from the Friedrich Alexander University in Erlangen, where they have proven that beam shaping could be really helpful to have a more robust processing, so a more stable processing. The melt pool is less dynamics. These are the slides we will see later. The second topic is productivity. Everyone is talking about productivity. We need faster processes. We need to increase the production rate. And therefore, we have one really nice showcase from DMG Mori, from Niels. And the last topic is, and this is something from my point of view, the holy grail. With beam shaping, we can also change and tailor the microstructure. And this is something which no other technology can do at the end. We can tailor microstructure, we can define mechanical properties by different beam shapes, and there we have a great example from Econity. So I will hand over now and with the next slide to Richard, and he will explain to you and answer the first question. Is it helpful to use beam shaping to get a more stable processing? So Richard, what do you think?
Thank you very much, Katrin, for the question. What we started when we started with the idea of beam shaping and the process robustness, we said so. Robustness is also always linked with control. So what can we do to show that we really get an additional degree of control over our process? And so when we could step to the next slide, I'm afraid there will be some more clicks in. And yeah, when we now see on the left side and on the right side, normally everybody, when we use a ring shape, then you will also see a spherical melt pool. This is quite intuitive, but when you show that we have a cubic or a rhombus-shaped one, then you, in the right side, it's a little bit easier to see it. And when you, for the cubic one, you also have a straight cut at the start. So you really have also a cubic melt pool, or at least as far, close as this goes to cubic. And this is nice to show that we really can have, we really can define the shape of our melt pool, not just the dynamics happening in the profile. So when I guess we need some more clicks now, because this is just zoomed in to better see it, that there is really, again, one, I will say stop, maybe it's easier that way. Sorry. And again, well.
Yeah, but actually it's quite impressive that you can tailor also the shape of your melt pool at the end and the dynamics. We've seen it in the videos.
And to the topic of dynamics, we come here now. This is just the dynamic beam shaping part. So both lines, same power, straight line. And when this is now about changing the intensity distribution over time. On the left side, good, stable profile you could use for every powder bed process. On the right side, same profile, same parameters, same straight scanning line, but now you see by changing our beam shape dynamically, we can make it draw lines. And these are perfectly timed. This is all of these single serpentines lines are exactly 1 millimeter in diameter. So this is for a closed loop control to maybe change it's now on this next slide. So here you see this is a Gaussian beam profile now. When we say no, it's about, and this you see the melt, it starts already to overheat. We have a very strong vapor plume. And now we can also use the same effect by changing the beam profile over time to kind of stir our melt pool. And you see same parameters, you see the reflection on the surfaces, but you see no vapor plume, no overheating in the melt. And then this also kicks in with the tailoring of the microstructure by a very strong control over temperature development.
Yeah.
And that was it from the LPT side. Thank you very much for the...
Thanks, Richard. And what we have seen, I think the technology, maybe you have recognized it, was something different. So there they used coherent beam combining, where you can actually create every beam shape you would like to create at the end. Maybe you would like to add something in terms of process robustness? We've seen also the beam profile was quite big, right? So the diameter or the size has also changed, right?
The diameter is actually 100 microns, so it's a normal, it's just a high magnification in this case. So, but
okay. Is there already a question?
Yeah.
Okay, but if there is a question, just raise your hand. I will have a look.
Yeah.
Okay. Ah, yeah. Therefore, we need also the mic. Maybe you can, Rob, can you give it? He has a question.
Yeah, please. Hi, yes, so you said beam combining there. Which technology is doing that?
Coherent beam combining, it's actually...
That's the company.
Sorry? No, that's the company name is Sivan in this case. Yeah.
Okay. So, I mean, the challenge if you have a tool like beam shaping is actually the question, where do you start? Yeah. So if you have a whole variety of possibilities, you can spend generations of PhD students just to get done with the first step. So the main question is what kind of defect or effect do we have that we want to get rid of, for example. And one is the, let's say, classic overheating in the middle of the melt pool if we have a classical Gaussian or defocused Gaussian beam profile. So actually what you want to do is you want to get a more homogeneous temperature distribution within your melt pool to avoid also dynamic flow or chemical gradients, stuff like that. And then basically what you have to think about is where would the heat go if I don't have energy input at a certain area. So basically you put energy in where you need it and let heat conduction do the rest. And what you've shown is that it basically works directly because you have less spatter generation and less fumes, less evaporation basically.
Yeah, and what you have also seen is that you create less bloom, so which means you have less vapor formation. This means also I would assume that the process is more efficient, right? So because all of the energy you apply to the material is directly into melting without any evaporation of the material. So I think this is another benefit, and the videos were really, really impressive and really nice.
Thank you very much.
Another topic is, and this is something I think all of you are also thinking about, okay, now we have these new possibilities, and the new possibilities also gives us the freedom, hopefully, to increase the production speed. And therefore, we have one really nice example from DMG, and maybe, Niels, you would like to explain it shortly.
Yeah, Katrin, thank you. Yeah, so of course, reliability and process stability is a prerequisite, right? And then once you get to that stage, the question becomes, what does this tool actually do for us? And productivity is a really interesting aspect for the ring mode laser. So it allows us to combine a profile either from a single spot or all the way to a ring mode that has 3 times the diameter, and therefore you can lay down a lot of volume at the same time. And then in between you have 5 discrete indexes that allow you to combine an intensity between the single spot and the larger ring, and therefore also change the diameter of the spot. What does that mean in production terms? Well, I'd like to compare that actually to a machining center. If you have a machining center, you have one machine with an envelope and you have multiple tools, right? We have ball mills that allow us to finish a contour, that allow us to make complex filigree geometries. At the same time, we have end mills that allow us to machine away a lot of material in a short amount of time. And so the ring mode laser from nLIGHT is actually introducing a similar effect here. Depending on the part geometry, we can either focus on very filigree lattice structures, for example, and use the singular spot. Or if we have fairly bulky parts, like the wheel carrier here, we utilize the higher productivity of the ring mode laser and only work with the ring. In reality, most parts will have some features that are filigree and that at the same time require more volume buildup. And there we can make use of the different indexes in between. And in this example, the heat exchanger, so you see the shell is rather thick, and there we need to lay down a lot of volume, whereas the gyroid structure on the inside can be fairly filigree with those thinner wall thicknesses. And we've done a preemptive study here on the example of this blow mold. And we used 3 indexes, so that's really where we can leverage that advantage of having multiple tools in the toolbox.
Yeah, maybe a question. I think a lot of the people from the audience have this question. So now we have the new design freedom in beam shaping. What is about software? At the moment, you talked about slicing. Slicing is really something you can just adjust the contour maybe and the infill. But how do you deal with the topic that you have now 6 different beam profiles? And from the software side, you have to choose, okay, what beam profile is the perfect one? Do you have solutions there, maybe to Econity and DMG?
Well, currently there is no option in commercial data preparation software where you can just select the beam profile. So basically, we are currently in the stage of evaluating which beam profile is suitable for what case, and then this will, I guess, step by step be implemented in the common build processors. So basically, it's just like you have a build profile for lattice structures, you have a build profile for more complex parts. And I mean, what is important here is that normally your part quality has to be defined at some point, and even if you machine parts afterwards, you choose your parameter set depending on the best surface quality that you need for that part. But that also means that you have great surfaces, or for LPBF, great surfaces in areas that are machined afterwards. So basically, if you can just print them faster, regardless of the surface quality, because it's a sealing surface or an interface where you machine it, then you can basically increase productivity without taking care of the part quality and that surface quality in that area.
But this also means you have to define different areas in one part, right?
Of course. Yeah.
Yeah, it's a great question that we often get, and Florian, you're hitting the nail on the head here. There's no commercial software available yet. So what we had to do, we had to start designing the control to match this laser, and we started designing our own software to allow us to utilize this laser. And I want to draw the analog of the machine tool, where if you machine a part today, you specify in your NC code which tool you machine the surface with. So you're defining in the code, you're defining the tool that you're using for each surface, for each machining operation. And the control and the software that we develop essentially does the same. The programmer will choose which feature will be built with what index of the laser. And you can modify that on the machine control as well as in the software for programming the parts.
That sounds very good. And can you say something about, is the software already available, or is it something you're working on at the moment?
So the software is as available as the machine is. So we have the first prototypes that are running, and deliveries are going out next year. So we have the control and the software in use at the moment together with the machine.
Okay. Yeah, very nice. Some question from the audience regarding this topic, increased productivity. I would assume for different materials it's also different. This was for aluminium, right? Do you have numbers for other materials, or some of you have numbers for other materials?
We have some experience with Inconel, a very common material. There's a lot of data public as well, and so we collected quite a lot of interest in Inconel. And we're currently evaluating tool steels. The big interest there is tool steels are today difficult to make in a powder bed with the powder bed technology, and the shaping of the laser profile and utilizing this intensity profile might allow us to print tool steels that we cannot build with Gaussian laser beams.
Oh, okay. And there was also one discussion round, I think it was the first one on Tuesday, right? Or on Monday, where they have talked about materials which are hard to print or hard to weld. And that it is also helpful to use different beam profiles, different shapes to manufacture these materials. I think the video will be available on YouTube at some point. If you're interested in that, I think this is also quite nice to see. Yeah. But maybe another follow-up question. Productivity, I think everyone is interested into productivity, right? Do you think the number you post here, 3 times faster, is it the limit, or do you think there is, you can even reach higher production rates or avoid post-processing steps afterwards, for example?
Yeah. It's a good question. It's a question we're asking and we're investigating. From the tests we're seeing so far, we have values where we have proven out basically a factor up to 3. Okay. And then it depends how you look at productivity, because of course one thing is the laser, and then the other thing is to really look into the process end to end. What does it take to turn around builds? What does it take? How easy is it to use this, right? And we're taking that into account as well. But yeah, so a factor of 3 we have proven at the moment, and of course we're asking the question: how can we push the envelope, and how can we possibly increase that in the future?
Maybe one aspect that I like to add here, the challenge is not necessarily only to print as fast as you can, because you can also use even more kilowatts and larger spots, but the challenge is when you change your intensity distribution or your laser powers or your parameters in general, you also affect the solidification conditions and thus the mechanical properties. And if you use different tools and different strategy within a single part, at some point, especially in tools or in tool steels, you do not want to have significant differences in the microstructure in one part if you apply a heat treatment afterwards. So basically, the question is, how fast can we go without changing the microstructure too much for our application? And this balances out, so you can print also, or you can melt 4 to 5 or 8 times the material, but then you have solid lumps of material with the microstructure that you do not necessarily want in your part. Okay. So that needs to be taken into account as well.
Yeah, I agree with you there. So is there now a question from the audience maybe? Yeah? No worries, we have a mic here.
Yeah, I've got a question really about, I'd like to know more about specific applications for the tailored microstructures. You know, what parts, what uses of this capability can you think of?
I have one example in one of the next slides.
Yeah, I think now this is really there. Maybe we have here, Rob, we have another question.
So, quick question from my side. When I have a part, let's say a heat exchanger with a bulky outer shell and a very fine inner structure, is it possible to set a different beam shape, let's say for the inner structure and the outer bulk material in one model? So I'm talking about the data preparation for now. So can I give a specific parameter to one area, or do I have to split my part, my model, into 2 or 3 sections and give the parameter to each section of the part itself?
Yeah, so it's similar like you normally specify your hatching and your contour. For example, you can define different parameter sets. And in a similar fashion, we can not only assign a parameter set, but we can also assign then an index. So basically, the index becomes a parameter in the software.
So does this mean that I only need one model? So like one STL file, or do I have to split to give the certain indices to different areas of the part?
Yeah, so in the model, like a step file, for example, I think we prefer step files, but in the step file, you work in one model and then you assign certain sections, certain areas with the index and the parameter set.
So this basically mean I only need one model and then I can assign.
Yeah.
Great.
So at the moment, with standard software, I think you have to cheat around a little bit, like you mentioned, to separate the parts in 2 parts. But actually, that's the topic, to work also on the software topic, to be able to have this new degree of freedom to say, okay, this area, this surface, for example, downskin surfaces or something like that, should be exposed with index XYZ, and the other area with another index. So I think this is a topic also Econity and DMG is working on, and also other system manufacturers or software manufacturers. But it was a very nice question from your side, and actually this is our next big topic, let's say. I mentioned it at the beginning. So when we talk also to customers and to partners, the question always arises, what are the benefits of beam shaping? And from my point of view, this is really the advanced thing to do and the holy grail more, that we are also able to tailor the microstructure. And sometimes it's not something we would like to do, but for some applications, tailoring the microstructure is really great. Think about if you would like to have, or you have a turbine plate and would like to have a very, very good creep resistance, then it would be great to have grains which are quite big in one dimension. And the question is this possible with beam shaping? And there we have one really nice example from Econity. So, okay. Florian.
Yeah, so there's a bit of data on that slide. Let me try to sum it up. So basically we found when we played around with the AFX for the first time, after we found stable parameter sets, what we compared is we compared the Gaussian mode to the ring mode on the right-hand side and something in between the index tree. What we did is we defocused the Gaussian beam to the same diameter so that we compare really the influence of the intensity distribution and not intensity distribution plus spot size. And what we found is that we had better mechanical properties, slightly better mechanical properties for the index 6, which we couldn't explain it in the first place. So we looked at the microstructure, we looked at the porosity, we looked at segregation behavior, alloy composition. Everything was pretty similar, but at some point we found out that what you can see on the bottom side of the slide is that the texture is significantly different. So we have a very sharp defined texture with columnar grains for the index 6, while we have something like more uniform grain distribution for the index 0 or even for the defocused one. So typically what you would expect if you use the standard index 0, which is a factor 3 smaller, you would have even finer grains. So that's just important to have in mind for the comparison. And what's interesting is, if you see something like that on the right-hand side, you would expect to be the mechanical properties like highly anisotropic. So basically in one direction you have high strength, but in the other one you wouldn't expect. But as you can see, there are slight differences between horizontal and vertical samples, but not as big as you would expect. So typically what we have here is a sharp texture that is not affecting the tensile strength in the direction perpendicular to it. And those samples are heat treated. So the tensile tests were performed at room temperature, but the samples were heat treated. So actually this effect survives the standard heat treatment for Inconel 718. And I think on the next slide should be an example. So those were individual samples that we built, but then we thought, well, we can change the beam profile in milliseconds. So what we could do is we could apply, as was explained in one part, different strategies. So this is an application that we made up in our head, but we thought it could be a good example to show where you could use it. So if you have a turbine blade, basically in the bottom part, what you have is some more or less uniform stress, but in the actual blade, what you want to have is basically a texture that is more or less parallel to your load direction. And then you can see that this adaptation of microstructure is also possible within a single part. So, of course, you have a small interface area, several layers, but then this definition of the microstructure can prevail in the whole part. So what's currently going on our side is that we actually check the creep resistance and the fatigue for those parts, because it would be interesting to see if it affects the dynamic properties as well. But those tests, as you know, take a bit of time. Okay. And one last thing that I could add, I hope, Rob, if you can just switch to the next slide. Perfect. This is not necessarily related to microstructure, but more to productivity. So there are basically, it's a machine with two scanners, where we build one part with a Gaussian beam on the top side of the image and a ring mode beam on the bottom side, and the right video is just slowed down. So it's 600 frames per second for thermography, quite fast. For high-speed videos, ridiculously slow. But what you actually see is that there are less spatters generated with the ring mode. So this is an aluminum process with 120 microns layers, so high productivity, but also quite dirty. So we use this because you can actually see the reduction of spatters with your own eye without any software analysis behind it. And this is also related to the fact that we have less overheating in the middle of the melt pool, we have less evaporation, the whole process is calmer, so to speak, and this is one of the reasons why we can push productivity with a ring mode beam. It's not that the process itself is quicker, but we do not have the adverse effects of spatters that land on your part or on your areas that are not exposed yet, and then maybe you build those spatters and you do not melt them completely and you have a defect in your part. So if you have less spatters, you have less influence on parts that are not printed yet.
Mm-hmm. Yeah, so very impressive video, also a nice video, I think. Another topic is, if we talk about spatter, the gas flow is always something which is really important. Do you think then, if you choose another beam shape and produce less spatter, also, let's say, the gas flow within the chamber is something which is not that important? Maybe, do you have an impression, idea? I don't know.
Yeah, so the gas flow still remains very important, right? It has a huge impact on the build quality, and even though we are reducing the spatter and the fumes compared to a conventional laser, we're still adding productivity with each laser that we have in the system. So certainly you need to optimize your gas flow as well. And just by reducing fumes, we still have fumes. So yeah, the gas flow plays an important role. Yeah.
Okay.
The great thing is that if you have less spatters, you do not need to improve your gas flow, because if it works with the single mode beam, even at high powers, and you have less spatters, then you basically already have a good gas flow in your machine.
Yeah.
Maybe to cut in at a point, we did some tests considering this to get a number for this, because counting the spatters, we did this at some point, but we really wanted to get a feeling for a part 50 times 50 times 50. And therefore, since it's hard to track the spatters after they landed somewhere on the place, we used tungsten particles and then track those afterwards with our CT measurements, and really got to the point that when we used the index 5, so the ring mode, that we had in the mean a reduction of 75% of the spatters we found in the other parts. So the one was with the Gaussian beam profile, just where like a Christmas tree, a lot of particles inside, which actually worked quite well considering hardness. We found out this was more a side topic, but the other one really showed no contamination by the foreign particles.
For what material was this?
This was for Ti-64 in this case.
Okay. So we have seen as the video was for aluminium.
This
right?
one?
Yeah. So it's even for different types of materials, and I would assume aluminium is a quite dirty process, you mentioned it, and it's also highly dynamic with aluminium, since the viscosity is quite low. And the number was quite impressive with 75%. Yeah. Okay. Another question came up in my mind was regarding microstructure. You have shown this for Inconel, and this is one really nice example for Inconel, I think. Have you experience with other materials to tailor microstructure? Some of you, I think you work also with different aluminium and titanium grades.
We got in the direction, and it's not directly linked to but also connected to microstructure, especially with high strength aluminum alloys. We had 6082, which is very hot crack susceptible, and therefore when you have the dendrite formation speed, which is still not directly explained, but when we wanted to print these materials, we got at 5, maybe 6 cubic centimeters per hour when we use the Gaussian beam profile. And just by using the ring beam profile, this again, it goes into the direction of productivity. Then the factor 3 isn't enough. I gave it there. It really makes this material working in the first place. The factor could be more in the direction of 20 in this case. Then it's still acceptable build rate, but there you show just by controlling the energy input, you make it possible that this material solidifies without cracking during the solidification phase. So this is another point where it's really show the strength.
Yeah, and actually, every material that we've shown is a material that already exists. So what we try to do is, especially Inconel was developed for casting decades ago. So right now we are dealing with significantly different temperature time cycles for this material. And Skalmalloy is one example where material was developed to benefit from the fast cooling in LPBF. So we are also cooperating with material developers that right now try to exploit the possibility of adapting the melt pool shape, which basically gives you the opportunity to at least define the grain growth direction. And there might be materials that also then exploit this capability more in the future.
Which means we not only open, let's say, microstructure tailoring and formation, but also open up new possibilities for new materials, right? Yes. Since you have explained that you had less cracks or 0 cracks for the material.
You can bring it down to 0. You can avoid this, but just by processing the material so slow that it is reasonable to use anymore.
Okay. So this is also, from my point of view, another benefit. Does someone has experiments with materials which are hard to weld? We have seen that one, maybe another one. So we are working, for example, with tungsten and use beam shaping to manufacture tungsten to avoid cracks. This was also quite successful so far. I'm not sure if you have experience with
some Some tests currently in progress are with tool steel. I think I mentioned that before, and that actually confirms also what you are mentioning. Tool steels that might have not been possible before because of cracking are now becoming cracking. So in that regard, we're not necessarily comparing productivity, but we're actually considering a step change, where suddenly something becomes available, something becomes feasible that has been economically and technically not feasible in the past.
Okay.
Our experience with materials susceptible to cracking is that what drives those cracks is thermal gradients. And even if you have a ring mode or something in between, you are still dealing with a very small scale. So our first trials, this was not something very systematically, more like a quick and dirty, just try it out with Inconel 738LC, was that even with the ring mode outwards, so it was index 3 or 4, that it's not quite sufficient alone to reduce the cracking to 0. But if you combine that with the preheating, then you need less preheating temperature. So it can help that you don't need to have like advanced high temperature inductive heating, but you can use a conventional heating, for example, which might help to improve it. But it's a bit early to say that definitely at this time.
Okay, but nevertheless, very interesting. This would also mean maybe you can work with another system which has a lower preheating temperature, for example.
Yeah.
Okay. Is there a question from the audience? Someone here is a question? Or here, yeah, sorry. Sorry.
No worries. Hi.
Hi.
I was wondering if it's possible to do this ring mode with copper, or if the reflection is too high, because you need a lot of energy, like 1000 watt, and if it's possible to tailor the microstructure of copper with the ring mode.
So, has someone experience with copper?
Yeah, so from our standpoint, it ultimately comes down to energy density.
Yeah.
And so that's a combination of the spot diameter, the productivity, the layer heights. So copper is feasible with the ring mode, and then there's also various laser powers available. So it depends then how much laser power on the laser you choose if you want to increase really your layer heights, for example.
But the question was also a little bit in direction of tailoring microstructure, right? For copper, it would mean the conductivity would increase if you have a specific microstructure. Actually, we have done some investigations in this direction, but it's not like really systematically. There are some ways to tailor the microstructure for copper, but yeah, let's say it works, but not for all applications. So, yeah. But, yeah.
Thank you.
So,
but maybe one point added to the copper system, when you work on copper alloys, then you also know the problem with back reflection. There's very fast, very damaged machine, but just by using the ring shapes, you get a lot less of pressure on your optical system. This is really so you can use, without changing the wavelengths, you still can get an infrared laser to really work in additive manufacturing with copper, which is not given by when you're considering just a Gaussian beam profile. Then it would be better to switch to a blue or green wavelength.
And regardless of the ring shape, the 1.2 kilowatts in the Gaussian mode also help. So just give us more power, then it works.
Yeah, actually,
as
that's
long
all
as you
of
trust
our
your
wish,
optics.
right? Maybe that's a wish list for nLIGHT. Give us more power. We already talked about it.
I'm pretty sure they never heard this before.
So we have another question.
If each beam profile has different effects on the microstructure, spattering, different characteristics, both in the part and maybe even within each layer as we change through different beam profiles in a build, how does that affect the qualification and certification process? And have you spent any time trying to bring those tools up to speed, or the software up to speed to take that into effect, or into account?
Have you understood it?
Yes.
So the question was in direction of qualification and certification processes, right? If you change the different beam profiles and so on.
Right. If we're going to deal with different microstructures now, both within each individual layer and based on the feature size, the structure of each part, how does that affect the qualification process?
That's a good question, actually. Maybe someone of you would like to say something?
I mean, certainly there are many regulated and certified industries in the US, and the requirements for regulation, you need to prove out that your process is clearly defined and that it is repeatable. And frankly, I see with the just changing the laser tool, you just need to prove out that it's defined and that it's repeatable. And since you can control the indexes of the laser, that is given. So you can certify what index you use on which part.
And maybe an additional comment on that. So many industries are at the moment freezing processes for qualification and certification, which means you are not allowed to change anything, like you have to produce the part always on the same system, freezing parameters and so on. But actually also these industries are at the moment moving in the direction to certify and qualify the part and the part properties, and to also flexible adjust the building process again. And I think this is a really good direction and would be helpful to also tailor and use the different beam shapes on different features of the part, like downskin areas and so on. So I think there's also a movement in this area of certification and qualification processes.
Again, it's similar to machine tools, as you said. We are not certifying or qualifying the RPM of your spindle in your machine tool. What you qualify is the surface quality of the part. It's a bit different in LPBF because the material is generated during processing, but that would also mean that we need to think about new ways. What do we actually qualify? At some point for the operator, he typically shouldn't care about laser power and beam profile. He shouldn't care about what type of part comes out. And then basically it's a question of what analysis methods do I have available to make sure that my part is coming out in the quality that I need. Of course, this should be coupled with some machine integrated monitoring, but that might be a different topic. But again, qualifying the part is the right way. Qualifying what the machine does can lead to different effects.
Okay, is there another question? Maybe I have a question to the audience. So if you would like to change something on the powder bed fusion process, let's say you would like, or imagine you have the same temperature of the melt pool to get a more stable processing or something like this. What would it be for you? Maybe someone has an idea on that. So if you can change anything on the powder bed fusion process, what is the thing you would like to work on? And then maybe a solution could be a different beam profile. If there's no answer from the audience, maybe I'll ask you, what do you think, what should be changed? What is the next thing to work on in powder bed fusion?
I would start maybe in this case, because this is also to the industry from a consumer more to me. And I guess it comes back to software. A lot of it is software, because also when you say you want to qualify a part, then how do you do this? Because when you want to retry it, when you have a weird way by having a part which is one part, but you have to change it in different shells, giving this different parameters, or even worse, when you say you want tailored microstructure in a Z direction, then you have volumetrical shapes that you bulk together. And this is where I really see a lot of, and also with that, we had the rapid change of different beam profiles. And this comes again down to software. Maybe also this is at the end point, I guess this has to be linked in some form of closed loop control to get the full benefit out of it, because it's a very complex process, and knowing in advance which profile I need at which point is maybe a little, then it could still be easier to just try it.
Yeah.
But to get the full benefit out of it, I guess that we have to keep up in software.
Yeah. And I think what we need to change as an industry is that the technology becomes more available to the broad industry. When we walk around here at Formnext, I think we still see a lot of high-end applications. But that only represents the tip of the iceberg, so to say, right? That's a small percentage of the industry. I think what we need to change as software makers, as machine tool makers, and so on and so forth, we need to come up with ways to make it easier to use this technology, and then also make really a paradigm shift in the cost of this technology. Make it more accessible to companies that make more general applications. Make it more not only productive, but also reduce the cost per part in the end. To increase the ROI and make it attractive to take the risk and invest into this technology. So I believe in the future we will see a manufacturing environment where additive is just one tool set out of the one tool in the toolbox, right? You'll have machining, you'll have grinding, you'll have EDM and other technologies. And in order to get there, we really need to lower the entry hurdles, and we really need to make it attractive to invest into this technology.
Yeah. I agree with that. Maybe Florian?
Yeah, I also fully agree. And one other aspect that I would like to add is it is very time consuming to even try out the AFX with 7 different beam profiles. If I have tools that have a more or less infinite potential to influence the beam shape, then it's you can research for years and still not getting ahead. So I think what we also need is more process understanding in a way that we can combine the experimental part with predictive simulations that helps us in deciding, okay, what do I need to change in terms of beam profile or in terms of process parameters, so that I don't have to wait 6 months to have our samples back with fatigue values to find out that it didn't change at all. So this, I think, also will help to get the broad acceptance of the technology, because if you understand what influencing factors you have on the machine, then you can also enable customers to print parts not in the best quality possible, but in a sufficient quality for the application. This will drive down the costs and at the same time enable the acceptance of the technology.
Yeah, this was a really good point. Actually, we can have, I don't know, hundreds of PhDs working with completely different beam shapes. The new degrees of freedom are infinite at the moment, and I think this is challenging. But a good point from my point of view was also to combine this with really good and fast simulation tools, right? To predict in advance whether this beam shape could be helpful for our target value, whether the target value is productivity, robustness of the process, and therefore you need also different tools. Like if you would like to have a look on the dynamics of the melt pool, you need some simulation in terms of fluid dynamics to really understand that. So I think the combination of experiments combined also with simulation is one really important topic. So, do we have another question from someone? There we have one question.
Yeah, thanks. Very interesting discussion. And you keep talking about these tools in the toolbox. And so what I'm wondering is, I know that this laser was developed because of physics of fibers and so forth. But if we talk about just circularly symmetric beam shapes, are these the right 7 tools, or are there other tools that, laser manufacturers need to be generating for us?
Yeah, that's a good question. And actually, at the beginning, I explained that there are also different ways to shape the beam, and there are also ways to shape the beam completely free. And I think it depends again on the target value you're aiming for. If it's productivity, maybe just creating a ring-shaped beam with a large size is enough. But for example, what we have done, the idea was to get a really homogeneous temperature distribution of the melt pool and a rectangular shape of the weld seam to make a large hedge distance, and therefore we calculated a beam shape. So we calculated what would be the perfect beam shape, and this, of course, looks different compared to a ring shape. But I think the challenge is, again, what is the target value, and what is also the feature of the part and the material. I think it will always depend on these parameters. But the new design freedom is huge now, and I think to understand better what we can achieve with these new tools, is a first good step in the right direction. I'm not sure if you would like to add something there.
Yeah, and I would add that it's also always a question what is physically possible and what are we able to reproduce in a lab environment, and then what is actually proven out and what can we move into production. And so it depends whether the drive is to make the next step change and maybe develop something new, or whether we're really talking about going into production and then utilizing a concept that is proven out that it has the maturity level to move into production.
Yeah, and this is also, I think, a little bit combined. There are new tools, and you also have to have a look so the added value you bring into the process with the tools compared also to the cost. If one system then costs, I don't know, 3 million euros, I think it's also not feasible for new application fields, right? So it's always a trade-off. Yeah.
And also your question got in the direction of which process or which tool or what is the end product you want to use it for. I want to add in this context that is the ring shape a good profile? And I would say this is also then very material dependent again. And the more you go to, when you say this in physical terms, the faster melting, meaning a lower melting temperature, and the higher your heat conductivity of your material is, the more worth you will get out of the ring shape. You lose a lot of this power when you go in the direction of higher melting alloys. Then you can tweak a little bit, but the highest benefit of a ring shape you will see with low melting, high heat conductivity materials. So aluminum, copper, the ring really shines. Other materials, different question again.
One last aspect might be that the intensity profile is one tool in the toolbox. The number of spots, the deflection technology, or even something very basic like how do I apply my powder? I can do this synchronous I can synchronize exposure and powder deposition. So in terms of productivity or even temperature time cycles, we also have a different set of toolboxes where the intensity distribution has a certain influence, but once I found something that works in a small, so it works with a single spot, then I can also scale this typically as we do in multi-scanner machines or even some new array-based exposure strategies.
Okay. Another question from the audience? Everything is answered?
So there's, besides the intensity pattern, which you were talking about, there's other properties of light, for instance, the polarization. And I'm just wondering if that would come into play at any point, or if there's any research in that direction.
Yeah, actually, I know why you have asked, right? So you are from the Lawrence Livermore, and you have dealt with the topic of polarization. Yeah, I think this is interesting. We are not doing something in this direction, but I know your investigations, and they were quite interesting. I'm not sure if someone is changing the polarization direction to change. I think you have proven to change also microstructure or something. Yeah.
I don't know what the exact outcomes would be, but I'm just saying, like, we're looking mostly at the intensity pattern, which is what you're saying, and also scan speed or scanner types. But then would polarization be something that you might put on a machine in the future?
Someone would like to comment on that?
So we have not experimented with polarization for the actual melting. Where we do use it is for monitoring, because then you have some degrees of freedom to increase your image quality, but I don't think that this is what you were asking for. So we don't really have a set of experience to answer that question seriously.
Yeah, on that note, how does in situ monitoring change with these new lasers? Is it the same, the coaxial monitors and?
Mm-hmm. So it depends what type of monitoring you use. So if you have, let's say, single pixel sensors like photodiodes or pyrometric sensors, then typically your measurement spot is significantly larger than your actual melt pool. So the change in temperature distribution in the melt pool is not really captured by those monitoring systems. But what you can still detect is something like a mean temperature related value. And then, of course, what you can see actually is that the standard deviation of your sensor signal during exposure is lower, for example, for the ring mode. And this directly correlates to, let's say, less dynamic effects or less spatter generation in the melt pool itself.
But
Thanks, Ez.
yeah, thanks for the question. And I think there are a lot of things in photonics available which can be tested in additive manufacturing, and a lot of nice things to play around. And I think therefore also the universities are there to have a look what is new in this field and what can be tested. And that was actually the initial step. Together with nLIGHT, they said, okay, we have this new laser. You would like to try it? And I think it was quite similar with the other guys here. So, is there one final really important question? If there is no final question, maybe I have the last question to all of you. What do you think is the perfect beam profile? This is a really mean question, I know, but what do you think? So that's the final round here.
A flexible one.
Okay, a flexible one. Some other comment?
Changing is, I guess, also there's no one size fits all, I'm afraid.
I mean, we've seen that we don't have to fixate on one, so why should we?
Okay. Niels, you would like to add something?
Avoiding a straight answer as long as possible.
I'm curious how a line laser profile would change the melt pool characteristics if you could change the laser in the direction of the movement.
Yeah.
It's a curiosity.
Would be interesting, definitely. What I have seen, what was also really cool is, beside that one, beam splitting for laser welding, which was also quite impressive to change or split the beam in different beams and tailor really the keyhole in the different keyholes. I think this is also something which could be interesting, beside, of course, the AFX here. So, if there is no question, I think I can close the session. Or Rob, do you would like to say something? Yeah, and thank you to the audience also.
Thank you very much.
Thank you.
Thanks for the really, really great questions, actually. We had internally almost the same questions and discussions like you had today.